Hi, Assalamualaikum warahmatullahi wabarakatuh. We are from Group 2. We'll present about the experiment T3 and the title is about the Joule-Thomson effect. Okay, this is our group member. From this slide, we can see we have KHAIRUDIN HELMY. Second, myself, MOHAMAD HAFIZ bin FADZIL. And the last our group member is Ting. Okay, in this part, I will explain about what is it Joule-Thomson effect. Okay, the Joule-Thomson effect is actually refer to the temperature change experienced by a fluid as it moves through an isolated valve from a high pressure area to a low pressure area. According to Joule and Thomson theory, change in pressure in the valve can cause change in the temperature of the fluid. Uh, in the simple terms, we can understand that as the fluid travel through the valve, its temperature can either increase or decrease depending on the pressure change it encounter along the way. Okay, in the Joule-Thomson experiment, a fixed amount of gas initially has pressure P1, temperature T1, and volume V1. It gradually flow through a porous plug until it reach its final state on the opposite side on the plug, where it has pressure P2, temperature T2, and volume T2. Okay. Furthermore, the process is characterized by constant enthalpy H, where the initial enthalpy H1 is equals to the final enthalpy H2. Okay, this relationship can be expressed mathematically, like the equation that I have put at the slide. Okay, in this slide, I will explain about ideal gas and Joule-Thomson effect. Okay, an ideal gas is defined as a gas that has no intermolecular force present between individual atoms or molecules and obey the ideal gas law, which is PV equal to nRT. Okay, in ideal gas, changing pressure doesn't affect temperature, so the Joule-Thomson coefficient is zero. But in reality, no gas is truly ideal. Most real gas is actually cool down as they expand into a lower pressure. This behavior is described by van der Waals equation, which is uh, bracket P plus A over V square bracket V minus B equal to RT, where A and B are the constant of the gas. Okay, from the previous slide that I explained about van der Waals equation, uh, if the two constants are known, it can be shown that Joule-Thomson coefficient can be determined from the following equation, which is bracket 2A over RT minus B over Cp, where Cp is the specific heat of the gas at constant pressure. Okay, for this experiment, it have three objectives that we need to achieve. Firstly, to demonstrate the principle of gas cooling by expansion. Second, to demonstrate the throttling process. And third, to demonstrate the Joule-Thomson principle. Okay, this is the setup for the experiment Joule-Thomson effect. Okay, the apparatus that we need to provide is Joule-Thomson apparatus, temperature probes and digital meter, and lastly, carbon dioxide and natrium gas supplies. Okay, next we go to the procedure. Okay, actually, for this experiment, it have two part, which is first part, we use CO2 gas, and second part, we use natrium gas. Okay, First step, make sure all pressure valve, gas cylinder valve, reducing valve, and operating valve are tightly closed. Check the actual direction, which is clockwise or anti-clockwise, to turn the knob in order to close or to open the individual valve. Okay, second step, connect the rubber tubing from the CO2 steel cylinder to the Joule Thomson apparatus. Okay, third step, carefully open the cylinder valve and the operating valve by tuning the apparative knob clockwise until it stops. Check the pressure, check the pressure gauge readings. Okay, fourth step, carefully open the reducing valve and adjust it to get to the desired gas pressure. Start with maximum pressure P1 of 0.8 bar and record the value. Okay, next step is when the temperature readings have stabilized after about 10 minutes, after about 1 minute, press the delta T button on the digital meter and record the value. Okay, step 6, reduce the pressure P1 by 0.1 bar using the reducing valve and repeat step 5. Okay, last, repeat step 6 until P1 is equal to 0 bar and record all the data. Okay, and the next procedure is use natrium gas. Okay, actually, for this part, the procedure is quite not obviously, no, it's not quite different with the first procedure that we use carbon dioxide gas. So for this part, I will just put the point that I think that it's important to us to follow to conduct for this experiment, for this procedure. Okay, first of all, before we use natrium hydroxide, first step, we need to close all the pressure valve, which is like previous video that I said, like reducing valve, operating valve, and cylinder valve. Okay, after that, please disconnect the rubber tubing from the Joule Thomson apparatus, which is the rubber tube that we use is CO2 to replace with the natrium gas. Okay, so second step, connect the rubber tubing from the natrium steel cylinder to the Joule Thomson apparatus. Okay, the next step, until the step 5 is actually it's same with the previous step. Okay.
Okay, now I will continue on the data and analysis. Okay, so this is our data for this experiment. So we are observing two different gases, which are carbon dioxide and nitrogen. We are manipulating the pressure with uncertainty of plus minus 0.1 bar, and we observe the temperature difference with uncertainties of plus minus 0.01 degrees Celsius. So we decreasing the value of pressure with 0.1 difference from start from 0.8 from carbon dioxide to 0, and for nitrogen start from 0.9 until 0. The first analysis is plot graph of temperature difference versus pressure for both nitrogen and carbon dioxide. Okay, so this is the graph for temperature difference versus pressure for carbon dioxide. So we can see that the temperature difference is increasing linearly with pressure, and we can see that for pressure less than 0.1, the temperature difference is negative. Next, this is the graph for temperature difference versus pressure for nitrogen. So we can see that the temperature difference also increasing linearly with pressure, and we can see that for pressure less than 0.7, the temperature difference is negative, and after 0.7, the temperature difference is positive. So the next analysis is determine the Joule-Thomson coefficient mu for the gases and their uncertainties. So this is the least square methods for carbon dioxide graph. So we are calculating the gradient and y-intercept for the graph. So this is the least square method to find the gradients. First we find the delta, and then we use the formula to find gradient and y-intercept. So we got the gradient is 0.18 degrees Celsius per bar, and the y-intercept is negative 0.063 degrees Celsius. And now we calculate the variance and standard deviation to find the uncertainty for gradient and y-intercept. So we find that the uncertainty for gradient is 0.012 degrees Celsius per bar, and uncertainty for y-intercept is 0.06 degrees Celsius. So the value of gradient is 0.418 plus minus 0.012 degrees Celsius per bar, and the y-intercept is negative 0.063 plus minus 0.0006 degrees Celsius. And next is the least square methods for the graph of temperature difference versus pressure for nitrogen. So this is the calculated value for least square method. And then this is the formula to find the gradient uh, for the graph for nitrogen. So we got the gradient is 0.255 degree Celsius per bar, and the y-intercept is negative 0.245 degrees Celsius. Okay, next we find the variance and standard deviation to find the uncertainty for both gradient and y-intercept. So the uncertainty for gradient is 0.064 degree Celsius per bar, and the uncertainty for y-intercept is 0.034 degrees Celsius. And we can say that the gradient is 0.255 plus minus 0.063 degrees Celsius per bar, and the y-intercept is negative 0.245 plus minus 0.034 degrees Celsius. From equation 3, mu is equal to delta T over delta P, where mu is the gradient of graph delta T versus pressure. And the Joule-Thomson coefficient can also be defined as equation 4, which is mu equal to limit delta P to 0, delta T over delta P. So we can calculate the value of Joule-Thomson coefficient based on the gradient of of the graph delta T versus P. We have calculated the value of gradient using the least square method from the graph of delta T versus P, and we got the gradient is equal to value of Joule-Thomson coefficient. So the value of Joule-Thomson coefficient for carbon dioxide is 0.18 plus minus 0.012 degree Celsius over per bar, and the value for Joule-Thomson coefficient for nitrogen is 0.255 plus minus 0.063 degrees Celsius per bar. The third analysis is using equation 6 and constant given in the table. Calculate the coefficient and compare them with your experimental results at room temperature. So if the two constants A and B from van der Waals equation are known, Joule-Thomson coefficient can be determined from following equation 6, which is mu equal to 2A over RT minus B over Cp. So the constant A, B, and Cp was given as table below. So the value of A for carbon dioxide is 3.6, and for nitrogen is 1.4. Both units are Pascal meter 6 per mole squared. And the value for B for carbon dioxide is 42.7, and for nitrogen is 39.1, and the units is centimeter cube per mole. And value of Cp for carbon dioxide is 366.1, and for nitrogen is 288.9, and the units are joule per mole Kelvin. So from equation 6 and the value of constant given at the table for A, B, and Cp, we can calculate the value of Joule-Thomson coefficient at room temperature, which is 299 Kelvin. So the value of mu for carbon dioxide is 0.799 times 10 to the power of negative 5 Kelvin per Pascal. And for nitrogen, the value of mu is 0.376 times 10 to the power of negative 5 kilo per Pascal. Okay, so this is the comparison between experimental values with calculated value for both carbon dioxide and nitrogen. So for carbon dioxide, the value of Joule-Thomson coefficient experimental is 0.418 times 10 to the power of negative 5 Kelvin per Pascal, and for calculated value is 0.779 times 10 to the power of negative 5 Kelvin per Pascal, and the percentage error is 46.34%. For nitrogen, the experimental value is 0.255 times 10 to the power of negative 5 Kelvin per Pascal, and for the calculated value is 0.376 times 10 to the power of negative 5 Kelvin per Pascal, and the percentage error is 32.18%.
Next, we're going to look into the discussion part in this experiment. So we're going to discuss some issues in this experiment. So first of all, we're going to talk about the apparatus of this experiment. So the tube in this experiment is separated into two parts, which is a region with higher pressure P1 and another region with lower pressure P2 by a throttling valve in the middle. So throttling valve is any kind of flow restricting device that can cause a significant pressure drop in the fluid, such as adjustable valves, capillary tubes, and porous plugs. So the gas in the higher pressure region is pushed slowly towards the lower pressure region through the throttling point by piston 1. So the gas got into its final state when all the gas are transferred completely to the lower pressure region with final pressure P2. So each region has a temperature probe that are connected to digital meter to take the temperature reading in both regions. The temperature of the gas will be carefully monitored on both sides of the region. Pressure valves are used to control the pressure P1 in the higher pressure region by looking at the reading at pressure gauge. So in this experiment, CO2, carbon dioxide, and N2 nitrogen gas are used in this experiment. CO2 and N2 are both colorless and odorless gas, and both of these gases are non-flammable gas, which is safe to use in the experiment. Apart from that, CO2 and N2 are widely used in many food freezing applications. Joule-Thomson experiment is also a throttling process which will produce an effect called as Joule-Thomson effect. So gas is pumped at a steady rate through a lead pipe that was cleaned to create a contraction. The cooling effect was observed when the gas expanded from high pressure region to a lower pressure region. So a pressure drops happen without involving any work. The pressure drop in the fluid is accompanied by a large drop in temperature. Apart from that, Joule-Thomson experiment is also an adiabatic process. So an adiabatic process is defined as the thermodynamic process in which there is no exchange of heat from the system to its surrounding, neither during expansion nor during compression. So there are a few essential conditions for this adiabatic process to take place. The first one is the system must be perfectly insulated from the surrounding. The second one is the process must be carried out quickly so that there is no sufficient amount of time for heat transfer to take place. So in this experiment, Q will be equals to 0. The experiment also contains constant enthalpy. So enthalpy is the measurement of energy in thermodynamic system. The quantity of enthalpy is equals to the total content of heat of a system, which is equivalent to the system internal energy plus the product of volume and pressure. So, for example, in region 1, which is the higher pressure region, the enthalpy H1 is equals to U1, the internal energy for region 1, and P1V1, which is the work done on the gas in region 1. In the second region, which is region 2, the lower pressure region, the enthalpy H2 is equals to U2, the internal energy for region 2, and P2V2, work done on the gas in region 2. So, in this experiment, we say that the enthalpy is constant, which means that the enthalpy values at the inlet and exit of the throttling valve are always the same. That means that internal energy plus the flow energy or the work done is always constant. Hence, we will say that H1 is equals to H2, which is also equals to U1 plus P1V1 equals to U2 plus P2V2. Okay, so the next issues that we're going to discuss about is Joule-Thomson coefficient. So not all gases undergo a cooling effect upon expansion. Some gases, for example hydrogen and helium, they will experience a warming effect upon expansion under conditions near room temperature and pressure. The direction of the temperature change can be determined by measuring the Joule-Thomson coefficient, or given by the symbol mu. The coefficient has a definition of the ratio of the temperature decrease to the pressure drop at constant enthalpy. So, as we can see, the formula for the Joule-Thomson coefficient mu is equals to dT over dP at constant H, which is the enthalpy. Joule-Thomson coefficient is a measure of the change in temperature with pressure during a constant enthalpy process. So from the graph, we can see that the different values for Joule-Thomson coefficient in the graph. So when mu is smaller than 0, the gas will experience a warming effect, so the temperature will increase. When the mu is equal to 0, the temperature will remain constant from the beginning to the end of the experiment. When mu is larger than 0, the temperature will decrease, means that the gas will experience a cooling effect. So the Joule-Thomson coefficient for an ideal gas is always equal to 0, as the enthalpy of the ideal gas is dependent on the temperature. So what is an ideal gas? An ideal gas is an imaginary substance that obeys the relation PV equals to RT. Ideal gas are essential point mass moving in constant, random, straight line motion and only react through elastic collisions. However, real gas molecules must interact with one another. Van der Waals equation of state was introduced to improve the ideal gas equation of state by including the two factors that are not considered in the ideal gas model. The first one is the intermolecular attraction force, and the second one is the volume occupied by the molecule themselves. So the equation is the Van der Waals equation of state, which is P plus A over B squared, V minus B equals to RT. So from the formula, A over B squared accounts for the intermolecular forces, while B accounts for the volume occupied by the gas molecules. The term A over B squared refers to the attraction forces, which is the attraction will act like an additional pressure, and it is called cohesion pressure. The correction term B refers to the volume of the molecules, and it is called as co-volume. When constant A and B are known, the Joule-Thomson coefficient can be determined by the equation below, which is mu equals to 2A over RT minus B divided by Cp. So Cp is the specific heat capacity of gas at constant pressure. Specific heat capacity is the amount of energy required to increase the temperature of 1 kg substance by 1 Kelvin. From the experiment, the value of Joule-Thomson coefficient mu for CO2 is 0.418 times 10 power negative 5 Kelvin per Pascal, while the calculated value is 0.779 times 10 power negative 5 Kelvin per Pascal. If we compare the standard values with the experimental value, the percentage error is 46.34%. From the experiment, the value for Joule-Thomson coefficient mu for nitrogen gas is 0.255 times 10 power negative 5 Kelvin per Pascal, while the calculated value is 0.376 times 10 power negative 5 Kelvin per Pascal. If we compare them, we can see that the percentage error is 32.18%. There are some errors might occur during the experiment and affect the accuracy of the results. First, the rubber tubing from the Joule-Thomson apparatus is not connected firmly with the gas supplies. Second, the reading of the temperature was taken before the temperature reading was stabilized. So there are some precautions that can be taken to reduce the error. First, we have to make sure the rubber tubing from the Joule-Thomson apparatus is always connected firmly to the gas supply. Second, The reading of the temperature should be taken after the temperature reading has stabilized around 1 minute. So, as a conclusion, we can say that the principle of gas cooling by expansion is successfully demonstrated. Second, the throttling process is successfully demonstrated. And third, the Joule-Thomson principle is successfully demonstrated.